Good evening, ladies and gentlemen. Thank you for the opportunity to speak in front of the good folks here. Today, my topic today is the inadequate knowledge transfer causes maintenance issues on imported ships. So I'm going to share some of my real life experience doing maintenance job with you, and then present with you the issues that we come across, and then propose that we come up with some solutions for the future. I would like to start with introducing myself. As Phil just said, after graduating New South Wales University, I joined 123 Naval Architects, where mainly we were designing aluminium fast ferries, catamaran ferries. That's the mainly fast ferries, as you see in the harbour all the time. That's the Thames Clippers on the Thames River. For those years I lived in London, I never get a free ride on those Thames Clippers that I was not quite upset about. Besides those rather smaller ships, the White Rabbit, the 84-meter trimaran superyacht. When she was first built, she was the largest trimaran superyacht in the world, aluminium trimaran superyacht in the world. And then I left 123, moved to London to study advanced mechanical engineering, where I had exposure to gas turbine engines, rotor dynamics, stress analysis, vibration, and so on. And during the time, I enjoyed my studies, but also travel. Sometimes you would say wake up to a breakfast in Budapest, and by the afternoon be sitting on a marina in Villefranche-sur-Mer. So it's quite enjoyable time during those years. Unfortunately, or fortunately as well, I have to come back to work. So I joined Baker and Provan. I started as a project engineer, mainly working on those. If you can see over there, that's the boat crane on the Anzac frigate. So that's a better view. So that's the top part of that crane. They're being overhauled or being finished overhaul at the workshop. And also the multi-purpose cranes on the mine hunters. It's the first piece of equipment to take off when they do the maintenance period, and the last piece of equipment they put on. And they will not sail without that, because all the provisions depends on that to be loaded onto the ship. Now, put up your hands if you have heard Baker and Provan before. Oh, you don't have to pretend, but more than half, that's good. So we identify ourselves as mainly a manufacturing company. We offer fabrication and CNC machining and mechanical and hydraulic fitting and assembly. We have offices in Garden Island, East and West, serving the fleet, and head office in St. Mary's. That's our main manufacturing facility. And we have a workshop in Kuma supporting the Snowy Hydros. So what do we do in the defense marine industry? This is in the past, we have supplied this control shaft for the Collins class hydroplanes. As you can see, this is a rather large piece of turning. You've got tapers, you've got shoulders, those little slots, and the flats and threads. So it doesn't get more exciting than this when it comes to turning. So yeah, let's spend a moment to worship this magnificent piece of heavy precision turning and milling. Okay. Oh, actually, if you look at these here, these little curves, I reckon they are they call it Marquis pattern, because of interference on the thread with the camera. So with that pattern, you can actually estimate the distance between the shaft and the camera, if you're interested. So Neil, that can be your homework for tonight. Anyway, in the future, we will keep supporting the fleet. For instance, the Hunter class program, we'll be doing that through partnerships with the Type 26 OEMs. We know the Hunter class is based on Type 26. Bacon Provan will involve heavily into the manufacturing of the gantry cranes, and the deck cranes, doors, hatches, and scuttles, etc., etc. And besides manufacturing, we also carry out a lot of service work on the DDGs, the LSDs, and the AORs. Now, tonight I'm going to present you with 3 examples from my day-to-day work and show you the kind of issues we come across. There are safety device pressure settings, a bolted connection, and some hydraulic pipe replacement. But before that, there's one more thing before we start that I decided to add to this presentation, probably in the last couple of days. This is a phone app. It's called a Spectrum View, developed by Oxford Wade Research. Have you guys heard about that before? So the reason why I would like to share this with you is because of a recent experience. So this app can display a real-time spectrogram and a spectrogram and a spectral analyzer view. I started using this app when I was doing the advanced vibration engineering. So let me tell you the story. So that's the story. There are 3 recordings from my phone, from left to right, chronologically. Okay. So if you look at each of the graphs, on the horizontal axis, that's time in seconds. Probably that's the easier one. Time in seconds. The vertical view is the frequency in hertz, and the color is the noise level in decibels. So red means it's loud, and blue means it's quiet, right? So starting with the first one. So I was doing a cold machine inspection, so nothing's running. Took up my phone and saw that. So I know there's pump running. It's about 50 meters away. And I recognize this frequency being a multiple of that. You can see the dots. But that one looks rather odd to me, because I was not expecting another frequency just below that. So, so I took a second recording. Anyone can guess what happened between the first and the second? What's the difference? Can you make a guess? Turn the machine on. It's not raining. Anyone else? So I walk towards the noise. When I hear the noise, I walk towards the noise. So that's the difference between 50 meters away and 5 meters away. As you can see, these get louder. So the closer, the louder. So it's more red than this one. And also you can see these relatively higher pitch noises from 5 meters away. They don't quite make their way to 50 meters away. So obviously, that's a frequency that does exist. Then I walked even closer, went downstairs towards the pump, and discovered a cover plate with loose screws on it. So it's a loose plate. So once I had someone tightened up the plate, that frequency is gone. So it's so fascinating that with the help of the sound, we're 50 meters away out of sight on a different level. I could see, oh, something's wrong, and went there and found out that plate and tightened up the screws. That's why I would like to share this experience with you. Like, it's so easy. It's a free app, and so easy to have an extra dimension in our everyday work and discover problems otherwise went hidden. Because by just looking at the noise, at the start, but my ear wouldn't really tell any difference. But the spectrogram does tell. There's some other frequencies there. Anyway, finally, let's get back to the topic. So first example, this is a typical hydraulic schematic for a winch. This here is a safety device. For simplicity of this presentation, let's disregard that pilot line and consider this being a direct acting relief valve. So it's something like that, right? So it's got a little orifice there, closed by that poppet, and then pushed down by that spring. So as you can imagine, when pressure keeps building up here, it will overcome the spring and then release the pressure. So the further you wind down and then knob, the larger the force from the spring and higher pressure required to overcome and relieve it. So that's how you adjust the reef pressure. So in this, let's say on the winch, you put 100 kilos on the hook and then somehow release the brake. The load would like to drop. So it would like to turn this motor and will build up pressure here, right? So these are hydraulic flows, sorry. So you can imagine if when pressure is building up here, it will want to overcome that spring. Let's say if the pressure setting was too low, it may drop the load and cause damage or even injury. But if the pressure is set too high, it will not be able to protect the system or protect the equipment from being damaged. So in this scenario, we were given this winch from the customer to overhaul. That's fine. That we've been doing this for many years. We're quite familiar with that. But as we were finishing up, we realized we should look at the manufacturer's instructions on what pressure we should be setting for safe operation. And that's the what they say on menu. For a moment, you would think you could read Italian. So this is the Italian English for, we're not going to tell you the pressure, so don't do it yourself. So we are quite confident to put everything, clean everything and put together, but without that piece of information, we're not confident that it can be operated safely. So these are the kind of information should have been passed on when they deliver the equipment, rather than finding this when you have to overhaul the equipment. That's exactly what they wanted, I guess. Okay, now the second example. So the first one is rather simple. We just need to make a phone call, write an email saying, hey, what's the pressure? Can you please tell us? And they, most of the time, they're quite helpful on that respect. So that's the maintenance manual.
That's it.
Yes.
There's no data sheet.
No, they don't tell the actual number. So we have to chase up. But that was easy enough to chase up a number. It's from the good Italian folks. There's another example. This is a bolted connection you find on a superstructure of a certain ship. They are just the regular bolted connection. You torque it up to 1,500 Newton meters. The only difference is sometimes on some of these bolts, there is a superstructure flange, on a flange on a superstructure frame that's right up against it. But that's not a problem for in this instance. We found these bolts in real life to be rather corroded. So we reported that to the OEM, and obviously they recommended these to be replaced. So let's have a look at what the descriptions from the OEM say about these parts. Firstly, their relevant DIN standards telling us what they are. Their size, M27, not very common, but it should be okay. Grade 10.9, that's what you expect for a structural bolting. And that's coating, decrement 500. It's essentially a zinc flaking process that rated to 500 hours of saltwater spray. Now, the keywords. Appears we have enough information to identify what they are, what size they are, what coating there needs to be, and what grade they are. So it looks like we have all the information we need to replace these. But if you look at first let's look at the bolt and the washer. So it's European OEMs tend to nominate DIN standards, the German standards, for their parts, but we have ISO standards in Australia. So that one essentially an ISO 4014. The washer is essentially an ISO 7416. So they're quite easy to get, widely used in Australia. It's very easy. In Bacon Provan, those are the part numbers we use. So it's in a standard database. But if you look at the DIN 6330, that's not common. We don't use it here in Australia, or at least it's not what I used. When we try to find it, it's very hard. We have to get it from Spain. That takes 8 weeks to get, minimum, and with a very big price tag, because it has to be air freighted in. But let's think about this. Let's do a comparison between a DIN 6330 and ISO 4032, which is the most common standard hex nuts we find pretty much everywhere. The main difference you can see is the 6330 is thicker. That's about 1.5 D, whereas the 4032 is 0.8 D approximately, where D is the major diameter of the thread. So anyone think, what is the benefit of having a thicker nut? Do you think? Anyone else?
Purchase access is restricted.
What is it?
There's more of it to get to if the access is restricted.
Right, okay. Yeah. So let's see. According to ISO 898 Tech 1 2013, the proof load for the bolt is 381 kilonewtons. And the proof load for that standard nut is 486.5 kilonewtons. So that means the weakest link here is the bolt. By using a thicker nut, it's not going to increase its load bearing capacity because it's limited by the bolt itself. So we didn't find that, but because a standard nut is already higher than the bolt itself, so having a thicker nut is not really going to help us. So then I looked up the European design standards, EN 1993, Tech 1, Tech 8, 2005, section 3.8. It gives a slightly lower proof load figure, but it shows the same trend. It is the strength of the bolt that determines the load bearing capacity, not the nut. So what we did next, we went to the OEM because we are in-country agents of the OEM, so we have a direct contact between our engineering departments. So we had a consultation with them, and turned out this was used for better vibration resistance. That's the only reason why they use that. So going back and forth a few times, they eventually approved our proposal to use the ISO 7032, which is widely used in Australia. We actually use it quite often for our jobs for Sydney trains. Actually, they use that for other projects as well. Just in that context, it's known as the DIN 980.
If you're using the name ship, you then have to get an engineering change approval to change the design of the nut.
Yes, so we do that through the OEM.
But you're the agent, the OEM in Australia, you do that.
We would prefer getting their approval, but just we have very good communication with them. So normally we can hold meetings, or in any case, let's say if we send them inquiry this ARVO, we typically get a reply overnight. So there's no issue with that. So what are the benefits? Since we can source them locally now, we reduce the lead time from more than 8 weeks to a week or two, and really reliably. Reduce cost, of course, because the airfare is probably $1,000. Better performance, because the 6330 rely on more thread engagements, so you have more friction, whereas the 7032, it's got a little metal insert under there, and it's got a pressed thread on it, so providing a much robust locking mechanism. And also, there's a bonus, Neil. We can use shorter bolts.
There used to be a thing called good engineering practice. Good engineering practice always used to state that you had 3 clear threads protruding from the nut.
Yes.
Which is that's what you got there.
Yeah. So. Yeah, I think if we do it to scale, we will be saving about 10 millimeters of length.
So the extra or not, short bolts.
We'd buy shorter bolts. It's probably cheaper too, and lighter, so the bolt can go faster. And the real bonus here is, remember I said some of the bolts, they right up against the flange. Now we have a 10 mil gap. We can actually brush paint it.
How many of these situations are there?
I mean
That are affected.
oh,
How many? We're talking 100,000.
we're talking about 200 instances. And they.
This is looking horizontal or sideways?
This is as is. This is vertical up.
Why
Yeah.
the wall is facing down?
Good question. Sometimes they just can't fit from the top because there's that superstructure superstructure.
Seen on the ship, and sometimes this situation is occurring. The nut was missing because of corrosion, and everything was loose. Asking to modify the design. And then
Yeah. So in this instance, the OEM, because there's some instances they just can't get away with it because they can't really trim the frame on the upper deck, so they just have forced to feed the bolt from under, unless they redesign the ship, which is probably going to be a bigger exercise. So had we have done this in the manufacturing process, we wouldn't have to squeeze this last minute engineering review and change in a very short maintenance period. That was the takeaway from that example. Next one, hydraulic pipes. Was in one of my inspections. I had to climb up the ladder, have a look, and the wall thickness is about 4 millimeters on those, and the corrosion is more than 1 millimeter thick. So, not surprisingly, we have to make new pipes to replace. The new pipes, they must be produced by a Lloyd's certified mill with the rated pressure on the certificate. They must have equivalent material property and the same sizes. So let's first have a look at the material. Not surprisingly, the material is nominated as E355 normalized. E stands for Europe. It's quite common in Europe, but in Australia, we would have a 350 grade, 250 grade, whereas in Europe, they have steel like E355, E235, E215, for instance. So in terms of chemical composition, you can see they're very similar with the E355 has slightly lower content of manganese, phosphorus, and sulfur. And when it comes to mechanical property, they are marginally bigger in comparison to the 350 grade we find in Australia. As engineers, collectively, we are conservative. So we tend not to say, oh yeah, they look quite similar, so just use it. So we have to do a proper analysis and verify that we can actually. The working pressure, let's have a look. The maximum is 230 bar. Which I will be showing here. So these are the pipes the OEMs selected. As you can see from there, they're metric pipes. OD, ID, flow rate at 5 meters per second. Their rated maximum working pressure. And these two columns show you the working flow rate of that function and the working pressure. These are found in the hydraulic schematic. As you can see, that one is 100 liters per minute, but the pipe is rated to 53. And that one is 360. The pipe is rated to 272. And also another problem we have is, for historical reasons, we have more scheduled pipes here in Australia compared to metric pipes, what we found when we were trying to source pipes. So it's not that convenient. Nevertheless, I'll show you a plot. So I plotted some of the metric size pipes and scheduled pipes based on their maximum working pressure in bar and flow rate based on 5 meters per second flow velocity. And these black circles, they're metric sizes, and the red squares, they are scheduled sizes. And the double circles are the ones the OEM chose, as I shown in the previous slide. And you can see most of them around here. So let's zoom into this area. So max working pressure from 150 to 500 bar, and the flow rate from 0 to 700 bar. So if you zoom in, voila, the design space. So let's say if you're given a job to replace some pipes without giving you any other information, what you would do is you probably find that one and then try to find something next to it that you can source locally. So you probably get that. This one doesn't really have a friend around. This one, probably that one. That one, probably use that one if you have no other information. But a lot of the cases, customers don't like it when, let's say, we reduce the pressure rating by 20%. We say, oh, it's good to work. It's just 20% weaker. Without giving them a good reason, it's a very hard sell. But in this instance, however, we have the operating conditions. So if you look at it, the 20 by 2.5, which is here, the maximum flow rate is 100 liters per minute. So it's around there. So we can potentially use those two, the 25 by 2.5 and the 3/4 schedule 40 to substitute that 20 by 2.5. And for the 42 by 4, the maximum flow rate is 360 liters per minute. So it's around there. So the options are that one and that one, which is 50 by 6 and 1.5 inch schedule 80. But actually, in practice, you would rather use that one, which is the 50 by 5, because it's got a adequate flow rate and adequate pressure. And the last one for the return, you have a 60 by 3 or 2-inch schedule 40. So these are the choices we would take if we were to design it, given those operating conditions, right? So let's recap. The OEM chose those ones, the first column, but we believe it should be those. And you can see the first two are different, indicating there's a big knowledge gap. There's something they know we don't. Because we can't just bluntly say they made a mistake, because they may have other considerations that we are not aware of. And now, in order to carry on with the work properly, we would have to answer these questions. Can we use the Aussie 350 grade to substitute the Euro 355 grade? What is the design rationale? Instead of using 50 by 5, they use the 40 by 4, which where 50 by 5 looks like the obvious choice. And can we use schedule pipes to substitute the metric ones, because it's easier to get in Australia? But then considering if we use the 1.5 inch schedule 80 to replace the 50 by 5, we're reducing the flow rate by more than 10%. And the next
schedule 8 is pretty heavy wall thickness,
yeah.
isn't it?
Yeah, because for these large pipes, the larger the pipe, the more wall thickness required to get the same pressure. We wouldn't really worry if it's a small pipe. And then practically, we need to have those manufactured by a Lloyd's certified mill with pressure ratings on the certificate, and also a minimum order quantity. That's a very practical concern, because a lot of the mills we went in France, they say we can supply them 300 meters per size minimum, whereas the ship only requires 3 meters.
Like banks.
Please like and subscribe to hear the ending of the story. That's for our YouTube channel, if it's putting up on YouTube. You're welcome. So, these are the questions we're supposed to answer. So eventually, the end of the story, we supplied the pipes of the exact same specifications as they were. We sourced them from European suppliers. We established good relationship with some of them, so they were able to supply us those sizes, meet the Lloyd's requirement for quality and certification. And the best of all, they didn't require a minimum quantity. But as an engineer, it's somewhat disappointing because something as simple as hydraulic pipes, we have to source from overseas. And in the future, if something like that comes up again, we'll be hit with the same long lead time and cost, and just got to repeat every time. There's a bit of a disappointment on that respect. In summary, so today I presented 3 examples. One is about pressure settings on a safety device. One is regarding the local substitution for the DIN 6330 nuts. And the last one is supplying of metric pipes. And these are issues we came across because of inadequate knowledge transfer in the first place, causing us to do extra work to carry on with the job. And if you think about it, the material selection or certification, the rationale of certain design choices and localization, these are all the questions. It would be so much better if they're answered even before the construction began. And that brings us to the recommendations. I recommend, according for the industry and technical community, to come up with a process when we import ships and other equipment from overseas. Let's say, just for argument's sake, these processes should start with developing an Australian catalog for standard parts. For instance, these examples from the European OEMs, they always nominate the relevant standards on their descriptions. So they choose these parts in their own catalog. They don't go out of the catalog. And we can happily build ourselves based on well-established catalogs on the ISO standards or DIN standards or UNI. And also we should encourage our own industry to select these parts when they do design work locally. And when we import equipment ships from overseas, we should require the OEMs to supply parts from that catalog where possible.
OEMs charge you more than design.
Potentially, but then you can otherwise the cost will just flow down in the future when and it will be repeated. But that's a waste of our own economy when it comes, if we have to repeat the same process over and over again, whereas we could have done it right the first go, and then we can just do it locally. Because it's all about what we always talk about, our sovereign capability. So that's all part of it. We can't rely on overseas suppliers for simple things. Secondly, adopt a common standard for hydraulic connections. That also becomes an issue because of historical reasons. We have various systems parallel in Australia. We would definitely recommend the metric system to those well-established standards, because majority of the world's industry is metric, with the exception of the United States, which only accounts for about 18% of the manufacturing output. So, and besides, United States itself has become officially a metric country in 1988. It's just taking its time to transition out of the legacy. And then develop a manual checklist for knowledge transfer. To say every time when we have these equipment coming in, we appoint a knowledge transfer engineer who should be responsible for making sure the key technical parameters are recorded. The design rationales are all documented, and the detailed maintenance instructions have been developed. And this is such a big project that's not to be done by an individual. it has to be done with collaboration across the industry and the technical community. As I always say, I'm only here to plant the seed and we all grow the tree together.